And that works. The microphone will work. So we get started. Do your video too, or do you do the video and the mic? Well, I guess we can get started. You guys hear me? There is a microphone, but if you can hear it, we're good. Excellent. So yeah, today we're going to have this afternoon, we're going to have a FAST.Farm workshop. And this is actually the first time we've ever hosted a FAST.Farm workshop. So we're excited about that. We've done a lot of open FAST workshops in the past, but it's the first time we get to showcase FAST.Farm in a public setting. And be myself and Emmanuel Brandlard here from UMass as the leaders today. And I think I sent this email link last night, but yeah, the tiny URL there goes to a Google Drive, and you should be able to access this presentation as well as the demos that we'll be able to run in the workshop today. So please record that. And I always like just to get a sense of who's in the room. So just go around the room and yeah, name, where you're from, and level of experience with OpenFast and FAST.Farm would be appreciated. So yeah, I'm Jason from NREL, and I'm working on FAST.Farm for 9 years now, I guess, but still can't run Jupyter notebooks. At least it crashes my computer, but you know, that's what it is. Yes, good manual. Or you, yeah, go ahead. Let's go around the room.
I'm familiar with it. I mean, and and probably 6 months, it's gonna take the best. And who's about 30-year patients soon, then can't function with I use open passport program.
Okay.
I've done this since store. My name is Chintan Corporation, which is on the company. I used to use open passport. So first time to that. If I'm need from England, I've worked on FAST.Farm and I've used FAST.Farm quite a lot, but I've not proven very little that's on UK options. I'm Randall. I'm a master's student here at UTB. I've been using OpenFast and FAST.Farm for almost a year now. Been with some type of computer. Hello, this is Marshall. I PhD student at UT Dallas. To be honest, I have not used FAST.Farm, so I see these both as a chance to replicate.
I'm Jessica Mishra. I'm a senior-based student working with Dr. John Rupert. I know OpenFast very well, and last 1 year I'm working with FAST.Farm. And I've really a lot of interactions and communications with Dr. Bell. And I'm also building up some of the simulation setup on the papers and things like that. So I know a bit, like last 1 year I'm working in fast food, but not the know about economic facilities.
So I'm Sayed Salamullaxan. I'm a first year PhD student at UMass Amherst with Professor Lennon Branda. I know OpenPath, but I have little experience in FAST.Farm. So I'm just here to get a taste of OpenPath with FAST.Farm. So looking forward to it.
Hi, my name is Jose Mora. I'm a research fellow at UMass. I would say early intermediate in terms of open fast, fast one, not so much.
Hello, I'm Rafael. I'm from my Boston assistant professor. I used a tool called Dynamics, which is DWN with R2. I use it, so I never used FAST.Farm, so I saw this workshop, and of course, yeah, probably.
Hi, thanks. I'm an engineer at Natura in Rhode Island. And I have some FAST.Farm experiences, but I'm to learn more about like supercontrollers.
Great. Thank you for that. So a lot of good, yeah, definitely almost everyone using OpenFast and a little bit of FAST.Farm experience, and also a good mixture of industry and academia here. So excited about that. Agenda for today. So talk a bit about fundamental concepts before. This will be very interactive, so please get ready for that. Overview of just, high level OpenFast and FAST.Farm, then dive down into some of the details of the various workings of FAST.Farm. And then we'll start the hands-on session with example 0, just before the break. Talking then about the input file and some guidance on how to use FAST.Farm, and go through the rest of the examples. And then if there's time at the end, we'll just talk about where we're heading with the solver. Okay, fundamental concepts. So obviously power curve, we got cut in, we got rated, we got V out and V50. Obviously power trying to maximize up to rated, then held constant. And we do that by, first of all, varying the speed, say linearly with wind speed. That's to maintain tipsing ratio. After that, we, pitch the blades away to maintain constant power. A couple of diagrams to kind of showcase that, there's the CB curve, say for the NRAL 5 megawatt. So in region 2 there between in and out, you're trying to maintain a tipsing ratio. So constant speed, speed that increases linearly with wind speed. So constant tipsing ratio, and I say constant pitch, and then higher wind speeds occur, go down the curve, lower tip speed ratio to get to constant power. And so my first question is, so in this case, where is the maximum thrust if we're talking about steady uniform flow and no turbulence? So if the wind speed's changing slowly, where would the max thrust be? In, rated, out, or E50? Just talk about rotor thrust, for example. Where is it in that turbine? Rated, and why is that?
After that, you reduce some throttle pitch.
Right, I agree with you there. So this is the CT surface, and so thrust at peak performance is typically 8/9 or so, 0.9. And as you drop the pitch angle, actually if CT goes down, so your thrust coefficient is going down, but nevertheless, V squared on that still goes up, but you're still, basically you're losing thrust at high wind speeds. Maybe after shutdown, you eventually thrust starts going up, even if you feather the blades. There's a lot of sort of drag on that. Wind speed still going up, so you still may get higher thrust eventually. But then the next question is, so why do we have to shut down the turbine? Or if the thrust is highest as rated, why do we ever shut down? Why is that? Why, if thrust is highest at rated and it really goes down after rated, why do we ever shut down the turbine? For the, once you hit cut out to say V50, why would you ever shut it down? Actually, speed's held constant after rated, so it's not because they're spinning too fast. So why do you ever need to shut down? Yeah, well, you're still actually still rated power, so the power is still the same. Torque is still the same. Speed is still the same. High load? Yeah. What sort of load is high? Thrust is obviously lower. Lift, well, it's sort of in there. So it's really about so yeah, so it's not about means at all. That's the key. I guess it's all about fatigue. So what I'm not showing here is this is just showing the sort of mean, right? If you're talking about steady uniform flow, but as soon as you have turbulence, um, it's not that. So if we say start looking at turbulence, what is what is usually the standard deviation of the wind speed look like as a function of wind speed? Standard deviation constant, increase, decrease? Which way does it go? The standard deviation is large at the beginning, V in and gets smaller. I'll push back against that. Anyone else? Flip that. So actually, standard deviation tends to go up. TI, I think is what you're thinking of. TI tends to go down. And so that's because you take the standard deviation divided by the wind speed, and mean wind speed is very low, so the TI is very high. So yeah, TI is actually going down, but the standard deviation is going up, and that's really why you shut down, because yeah, that variation is so much larger. And so if you kind of add, the thrust plus or minus, say, some effect from standard deviation, uh, you know, the way I show it here, still cut out, maybe the fatigue is still lower, but eventually that fatigue is going to kill you. And that's why you shut down the machine. Next example I love is the simple. I love the simple example. So the mass spring damper system, mass M, damping C, stiffness K, and applied force F. My first question, of course, what's the equation of motion of that system? Just give me the equation of motion. What does it look like? Right, exactly. So what equation? F equals ma. That's the basic equation I want. What is it for that system? I'm hearing it. Excellent. So yeah, mass times acceleration plus the damping term, stiffness term equals the force. So F equals ma for that system. Great. And then my question, of course, is next is what is the difference between a resonance and an instability of that system? So I have a very simple mass spring damper. What's a resonance look like? Was that stored energy? What does it mean in terms of like the equations? So if I have just F, K, C, and M, what's a resonance look like? Actually, resonance has nothing to do. Well, the damping plays a role, but it's not directly in the fundamental equation I'm looking for. Exactly. So if the excitation frequency F matches the natural frequency of that mass spring damper system, then you got resonance. And what happens in resonance? Basically, so again, that excitation frequency matches my natural frequency. And if you sort of plot that out, basically leads to linear growth. Linear growth is pretty bad, but it's not the worst thing that could happen. So if you catch that, you can sort of, maybe change natural frequency, add damping, try to mitigate that. So it's bad, but actually instability is far worse than that. And what's an instability for that system mean? What do you have to do for, one of those terms to make it unstable? Negative damping, exactly. So if I make C negative and I do the same thing, boom, that thing's going to blow up, and it's going to blow up exponentially, which is far worse than linear. So definitely want to sort of get around what resonance is, or if you're in a resonance, you want to sort of pass through it quickly. You don't dwell on it. Instability you want to avoid, because that's boom, that's exponential. That's key there. Another one, rotational sampling of turbulence. No question here, but yeah, so a turbine spins through a turbulence field, and really what you see is on the blade, you'll see, of course, the mean load from the wind, but you'll then see a 1P, 2P, 3P, and that's because the blade's chopping through all that, and it's sampling at basically harmonics of its speed. And then in the drivetrain, and then the cell and the tower, you're really exciting at 0P, 3P, 6P. So you ever look at PSDs of your time series of OpenFast, you'll see these spikes show up. So you'll see natural frequencies and you'll show these excitation frequencies. Again, in the resonances is where these excitation frequencies align with your natural frequencies. And another thing maybe important there is as you get larger and larger turbines, you're spinning slower and slower, these frequencies are basically dropping. So they're all getting lower and lower. So keep that in mind. Now we take that to the farm level. So a little too far there. So now I have 3 turbines in a farm. That's showing a FAST.Farm simulation there of you kind of, I don't really show the turbines well. There's 3 turbines and the flow is moving from left to right. And so now if I say, look at a simple case, I'm not trying to steer the wake and I'm below rated wind speed, what does it look like for power? Which turbine sees the highest power? Which sees the lowest power? What's that? On power? I'll flip that on you. So the upstream turbine is going to see the highest power, right? It's going to get the full effect. Sorry, without wake steering, yes, without the wake steering. Start simple. So the upstream turbine is getting the most power, and the other turbines in the wake, so they're losing power off that. And what about thrust? What does thrust look like? Guesses? What's that? Same trend? Whoa, what happened there? It's like jumping on me. Same trend. The trend is the jump the way next slides. So I agree. Same trend. Thrust is high. So again, normally you'd say, well, fatigue is higher downstream, but thrust is actually lower. So what's going on? Exactly. So standard deviation now. That's what really changes. And if you're in the florist workshop, you don't care about any of this stuff. Only look about means. And here we're talking about loads. So standard deviation really matters. So about standard deviation, these things, I try to draw it as a sort of range. So the standard deviation, say, of power also goes up quite a bit. Standard deviation thrust goes up, and that's really the big problem. Is your fatigue loads are going way high. So the mean loads maybe going down, fatigue loads are going way up, and that could be a big concern downstream. Now, if I look at what you were trying to get at, wake steering. So again, I'm below rated, and I have wake steering. What does my power look like now? You change. What does the trend going to look like? Kind of the same? Is it more or less equal throughout the farm? More equal, yes. So if you look at it this time, so we're leaving, I should have showed it before and after, but yeah, so the power of turbine 2 actually, turbine 1 actually went down a bit because I purposely yawed the flow, but that made the wake diverge away, and I've made overall power level, more level throughout the farm. Same thing happened to thrust. What happens to loads? You said downstream decreases and upstream what? Right, exactly. And so what actually this does is it makes it much more level throughout the farm. You're adding asymmetry to that upstream turbines. You're increasing its fatigue load basically. But the wake is now hopefully missing a bit the downstream turbine, and those that's going to decrease, and the overall you're kind of leveling out loads. So actually, that's an overall net thing. I really thought wake steering is going to be bad for loads. It's actually on average it's reasonable, and so you can use a tool like FAST.Farm to figure that out. Yeah. Is the right? This is certainly maybe an ideal case when I'm showing 3 turbines or maybe showing 5 on the plot. But so yeah, I'm just trying to show the trends. But certainly, if you're trying to put some complicated wind farm arrangement, flow in directions, like these trends could obviously have local effects. Exactly, but that's why you use a tool like FAST.Farm is to sort of answer these questions. Maybe one more example of now I've taken the same case, but I've made it above rated. So now I say winds at 18 meters a second. What's my power look like? What's that? Pretty much constant? Exactly. What about thrust? Thrust reduces relative to the low rated, certainly. Where's the trend down the row? Exactly. Good point. Good intuition, Stevie. You're kind of look at that previous curve we showed. So the downstream turbines are now in the wake, so their wind speed's less, which means their mean thrust is higher. And so again, power is basically constant. Thrust is also fairly constant because that wake is also pretty much diminished at that point. CT is very low. So slightly increased, but not a whole lot. And then standard deviation again, fatigue could also be important. Talk about above rated cases. Yeah, it's not a big increase down the farm for that. Okay, so that's hopefully gets your mind around these things again after a long weekend or a little break from weather. Now we'll start jumping into the tools, OpenFast and FAST.Farm. Obviously, yeah, really what we're trying to do is analyze the various physics, so the aerodynamics of the system, the structural response of the system, hydrodynamics, we're talking about offshore wind, and of course the control system being a big part. It's not just a passive machine, it reacts to its environment through a controller. Yeah. Today we'll focus mostly on FAST.Farm. Just want to paint that in the context of the broader tools we have in the NREL DOE portfolio. And so that middle column there is really about the detailed design where you're running, say, OpenFast for a single turbine. FAST.Farm now takes that to the full farm level. But you pair that with, say, steady state models. I think if you're in the WISE workshop this morning, you're running Wisdom for steady state performance or maybe frequency domain type models. There's a Flores workshop going on right now, steady state, farm effects, no standard deviations at all there or fatigue, all sort of mean effects. And then, yeah, of course, the high fidelity is really about resolving as much physics as we can, say with CFD. And I would say this is very much interactive environments. We use a lot of the high fidelity, say, to generate inflow for the engineering models, as well as a lot of calibration and validation of the tools from high fidelity to low fidelity. And I think this is also where AI and machine learning will really come more into play, is how do we sort of train some surrogates that mimic what the high fidelity is doing. I would say the partnership is the other way as well, because we can run a lot more cases at the engineering fidelity. And so if we're trying to say propagate uncertainty through, much easier to do that with an engineering model. And so using that to say forward propagate high fidelity solutions as well is direction I see. But here we'll focus really on the farm level detailed design work. Tools enable advanced technology. So again, because we can't fully resolve all CFD and make that computationally efficient, in the end of the day, we have to simplify some of the physics, and you'll see a lot of those as we go through FAST.Farm. But we try to, based on theory, there's obviously fundamental theory there, based on the computational solutions that we sort of calibrated coefficients, say, of the model. We have an engineering model that can then sort of run all the cases we need to advance technology. And at the farm level, that's really about, trying to design, say, my wind farm, including fatigue, not just power, but also fatigue loads. And then, of course, all the implications on all the other technologies. If you're looking at new novel rotors or drivetrains or support structure, you can do all that at the farm level now with FAST.Farm. So OpenFast, just one slide here. Again, you guys are familiar with that. But yeah, you can run time domain simulations, all about nonlinear IUC like loads analysis type approaches. You can also pause the model at any point in time, linearize and extract like a state space equivalent ABCD system. And you see some of the key modules there of OpenFast. We won't go through these in detail, but BEM type aerodynamics, also up to free vortex wake, and OpenFast beam type structural models, with bending stiffness, EI, GJ type stiffness terms, and of course full hydroelasticity on the floater as well. We won't dive too much into that today. Some of the key things in the framework that I think are still very useful when we talk about FAST.Farm are summarized here, because FAST.Farm is based on the same framework of OpenFast. So to understand FAST.Farm, we really need to understand the modular architecture of OpenFast. And so we have, first of all, everything sort of decomposed in the model in terms of modules. And those modules really have four main components to them. They have internally, they have states and they have parameters. So parameters are like the constants of the model that don't change, and states are what you need to know to calculate the things at the next time step. So sort of memory of the model is what's stored in the state. Inputs are what are calculated from other modules and being sent to a given module. So that's what this module needs to do its solve based on information that's external. And the outputs are what it's calculating for the purpose of other modules. Use that very much context for FAST.Farm as well. And as we go through FAST.Farm, we'll explain, what are the inputs, what are the outputs, what are the states and parameters of that model. The states in the model, again, this is like the memory of the model. They can be in really three forms. One is continuous time. That's the ODEs that we showed, say, before for the mass spring damper model. You can also have discrete time form where it's really a time step by time step solve. So given things now, I can figure out what it is the next time step, but there's nothing sort of continuous in between. Often you can take a continuous function and solve it numerically with discrete time formulation. And there's constraint like the algebraic constraints of the solve. And other states, sometimes we show up things like binary states and so on. Loose and tight coupling, that's illustrated in the images there. Loose coupling, we just mean that the module itself has its own integrator in it to track and solve its own states. Tight coupling, we mean there's one integrator that sort of integrates everyone's states together. And I presented on that a couple of years ago at NAWEA, tight coupling. And actually the 5.0 of OpenFast is coming out. I was hoping to announce it here at the workshop, but not quite. So in a few weeks, we'll introduce 5.0 of OpenFast that has a tight coupling option, which really makes beam dying a lot faster. Anyways, mostly when we're talking about FAST.Farm, we're actually talking about loose and loose coupling with discrete states. That's mostly what FAST.Farm is. Independent time and spatial discretizations, won't talk too much about that. Let's see, linearization, won't really talk about today. Data encapsulation and dynamic allocation are really important. That means we can basically create multiple copies of these modules and have as many as we want, and also have, say, the driver control its memory. Visualization capability we'll touch on here, and checkpoint restart becomes pretty important when you talk about FAST.Farm. We're talking about a big simulation that runs, that may take hours or even days if it's long enough. Checkpoints really useful to say I can pause the modeling point in time and then restart at that point in case my HPC goes down or something. These are all sort of built in behind the scenes of FAST.Farm. But now jumping into FAST.Farm. So the main idea here is that, I want to take the idea of OpenFast that we do all the time now for single turbines and say, I won't really want to have that for the farm effect. See if the animation here shows up. It actually does. So this is a example of FAST.Farm simulation with 36 turbines at the King Plains Wind Farm. That's part of the Awaken experiment, if you've involved in that in any way. But yeah, so the idea is to have one instance of OpenFast for every turbine, and then modules, and we'll get into the details of those modules that solve the wake propagation, the wake evolution, the wake meandering, wake merging, and that's all part of the solve of FAST.Farm. So we'll jump into those as we go forward. Just make two more points before we dig into the details. One is on verification validation. I think this is sort of central to when we talk about OpenFast or FAST.Farm, because we're not fully resolving all physics. It's really important to either calibrate the model against some high fidelity solution, and then finally at the end of the day, validate it. So the reality of interest could be a high fidelity CFD solution. It could be measured data from a real wind farm. But the validation is really critical, I would say, in tools like this, because there's a lot of these parameters that can be case dependent. So also pairing it with high fidelity is quite critical, with the goal, again, of using these tools for advancing technology. Finally, just one comment. This is all public open source data under an Apache 2.0 license. And that simply means that we're indemnified. So if you use the turbine and you use the software and it doesn't work for some reason, you can't sue us because you basically have to agree to this license. It's also fully open source, meaning you can take the code and repurpose it for anything. You can even resell it. We can't stop you from doing that. It's a very permissive open source license. But yes, but maybe they stop there and ask any questions before we dive into details of what's going on inside FAST.Farm. Anything yet? No. Okay, let's dive into the various modules of FAST.Farm. First of all, a little background, and I apologize for the slides. I had a bunch of old slides in the old 4x3 format, and I was like, I can't, didn't have time to upgrade them all to 16 by 9. So hopefully next workshop, I'll fix all those old slides. So sorry about the black bars there. But yeah, FAST.Farm overall is based on this dynamic wake meandering uh, framework that was originally developed out of DTU with 3 main subcomponents to the model. Overall, I would say we rely on some of the basic principles of that, but we've taken a number of advancements relative to, say, dynamics that's been developed out of DTU. So first of all, one is the wake deficit evolution. That's the main part of FAST.Farm that says, okay, if I'm at a, I generate my thrust and torque, say at the rotor, what does that mean in terms of the wake evolution from near wake to far wake? To make that solve much more efficient, we sort of skip over this pressure gradient zone where the pressure is recovering to free stream. We do that with this near wake correction model. We'll dive into what that looks like. Yeah, so that sort of skips over the sort of near wake region, and I would say that's where FAST.Farm is the most inaccurate, is in the near wake. So if we're talking about 0 to 3 or 4D, I wouldn't tend to trust FAST.Farm in that region. That's really the near wake correction is trying to get past that so that my far wake solution is accurate. So if you're talking about saying putting rotors very close together, a couple D apart, 1D apart, FAST.Farm would not be the tool for that. You really were trying to say beyond, say, 4D is where FAST.Farm would be accurate. Wake meandering takes that sort of deficit and meanders it left, right, up, down, based on large scale structures in the background flow. And you definitely saw that in that previous animation I showed where the wakes are sort of following the background flow. And really in that way, this is based on exactly the way it worked at DTU, is this passive tracer idea, and we'll talk about what that means. But basically it takes that nice uniform wake deficit and meanders it left and right. And then finally, we have this wake out of turbulence model, and really showing the 2 pictures there. This is showing for uniform inflow what it looks like with and without wake out of turbulence. Basically, wherever there's high shear in that flow, it adds a turbulence energy there, which of course can obviously be important for fatigue. So really the fatigue is driven by the 2 things, the meandering and the wake out of turbulence. Which one matters more depends on the case. Usually it's like for high TI, wake meandering is far more important. For very low TI, wake out of turbulence is much more important. And you talk about sort of medium TI, it's somewhere in between. So usually I'd say, at least if you're doing high TI cases, wake out of turbulence probably not too useful, may as well turn it off. But low TI, definitely it has to be there, or you're going to miss out on the main effects. Okay, some of the innovations, and we'll step through these as we go forward. But again, it's a very modular implementation of DWM. And so there's a number of advantages of that, because as we add new modules, we can basically make them options in the code. We've done a lot of work with doing LES generate inflow for, say, really important for larger and larger farms. The old GTU model was all based on MON, so a lot of LES inflow here is being used. Talk about some of the advancements made to the wake advection and deflection and merging. Yeah, we'll go through details there, but yeah, definitely we've made advancements there. Our wake out of turbulence is now at the farm level. The original implementation was very much a local turbine effect. This is a farm level effect, so it's similar ideas, but extend to the farm level, and there's some advantages of doing it that way. I heard supercontroller mentioned as one need. Actually, Abba Need, I think, is working on a nice example for us. And so, yeah, we have interface right now for supercontroller, and we'll have a nice working example of that here soon. And then let's see, shared moorings, another advancement we've made in the last couple of years. So not being able to just interact turbines through wakes and control, but also through, saying a shared mooring arrangement in an offshore wind setting. So yeah, now wake turbines can tug on each other as well. So you'll see that where it shows up in the solve. The parallelization of the implementation has been done, and I'll showcase some advancements we've been making to that recently to make it a lot more efficient. And yeah, a lot of calibration against high fidelity models. So again, we'll step through those. First of all, some basics. basic terminology on FAST.Farm. Really operates on, I would say 3 main things you have to understand for the understanding the FAST.Farm solution. Is first of all, there's 2 inflow domains. One is what we call the low resolution domain, and this is a pretty coarse resolution around the whole farm. So wherever there's going to be a wake in the farm, you have to put this domain in there because it's what sort of does the meandering of the calculation. So that's a course both in time and in space, and we'll give you guidance on what the time steps and space requirements need to be. But that's a really coarse, usually a couple seconds on time step, and 20 to 30 meters, say, for spatial resolution, but it depends on the case, I guess. And then there's also high fidelity domains, and this is really because the OpenFast solve or whatever elastic solve you're having needs a pretty high resolution inflow. So you're talking about hertz for time scale, and say chord length for spatial scale. And for the elastic solve to get an accurate inflow, it needs that high resolution. So we really split out FAST.Farm that way to have the 2 domains solve things like that. So we capture best of both worlds. If you made the low resolution at the same res as high resolution, it would obviously work, but it'd be much more computationally expensive. And then the final thing to keep a track here is the wake planes. So this is where all the wake dynamics calculations are done. We basically calculate, what's the wake deficit at the rotor from our thrust, and then that wake plane gets propagated downstream and meanders with the background turbulence. But all the basic calculations are done on these planes. So that basically discretizes how we solve the wake. One thing you see also in this image is, you can have overlap. So planes can overlap if multiple wakes are hitting the same, point in space, and we call sort of distance between the planes the wake volume. But yeah, that where the volumes overlap, that's where we do a superposition type approach, and we'll get into the details of how that works. So first of all, I guess we'll step through here various modules of FAST.Farm, and we'll sort of work our way from the top to the bottom, and then talk about how the driver code works as we step through. So at the very top, of course, is OpenFast. That's what's doing the turbine elastic solve. Behind that is the controllers of OpenFast, and I made them dash because they're usually compiled a bit separately, say, for the rest of the solve. The rest of the thing is compiled in one big executable. But the controller is usually compiled separately as a DLL, and the way our supercontroller works is it interacts with that DLL. We'll just describe briefly how that works. We have an instance of Moordyne at the farm level. So, of course, OpenFast has Moordyne in it. With the farm level version of Moordyne, that's really to get all the shared mooring effect that we just mentioned. And then we have wake dynamics. What wake dynamics is doing is solving the wake off one of the turbines and propagating that wake deficit downstream. And then the ambient wind array effects module, that's really what sort of loops through that whole low res domain and does the wake superposition, the wake deficit calculation. It will also calculate the velocities of the wake planes for the next time step. So hopefully that gives you a big sense of what the code looks like, and then we'll step through. Again, OpenFast, not much to say here. You can see it in the modular structure at the top. Its inputs are pretty limited, actually. Obviously, a lot of stuff is inside OpenFast. We have whole workshops on that topic. But in terms of what FAST.Farm does, is it says, here's the disturbed wind. So that green box I showed earlier, the high-res domain, it says, here's the wind for this, this time you need to solve. And it sends that disturbed wind field, including wake effects, into the OpenFast. And then for the shared mooring system react, we also basically have to send the Moordyne tensions across to each turbine. If you don't have shared moorings, that does not exist. The outputs, what OpenFast is calculating every time step is, where's this hub position orientation now? What's my rotor diameter and relative velocity and skew angle? It needs that for the wake solve. And then also the thrust and torque distribution needs to come out of there, and then the floater motion, again, if you have shared moorings. So, but because the interaction is pretty minimal, it's actually pretty easy to swap out OpenFast for other solves. So we've actually done this for some industry partners who weren't using OpenFast, but they were using some other code. And so popping out OpenFast, plugging in there another elastic code is not too hard. So if you ever want to do that, again, talk to us. We can give you guidance. But as you see, the connections to the solve is pretty minimal. One thing to keep in mind here is time steps again. Talking about the two different time steps for low and high res. Usually OpenFast is a much smaller time step than that. And so we do a lot of subcycling of the solve. So keep that in mind, and we'll talk a bit more about that as we go forward. Supercontroller, again, that module has really been evolving with work of Abinit recently. But right now we're basically fully relying on how we do it through our Discon interface and Roscoe. We've added this 0MQ protocol to basically transfer data from your controller and OpenFast, as well as controller and other controllers. Through that 0MQ data passing interface, we've now set it up so that works with our supercontroller. So Abinit is working on this reference supercontroller that has a combination, you correct me if I'm wrong, Abinit, but has a combination of like a consensus control algorithm and a wake steering algorithm. It'll basically become our reference open source controller for wind farms that you can then take and use for extending any sort of wind farm control setting. I don't know if you have any updates you want to share on that, Tom. I don't have much detail here, but it's just high level.
That contains set of reference controllers that can plug and play with any farm, and that is going to be released soon. And the idea is that if we have developed a set of controllers on our own that can scale sensors, the experience, and so on, and all you need to do is just like provide the farm, and the tool will design the controller for you and just plug and play. So right now, the low level Roscoe controller is working, works with FAST.Farm, the NAWEA. It is also working, but it will be released.
Oh, thanks for that. Sorry to put you on the spot there.
So we will import that. So that will be challenge to drop and use like to control that.
Cool. So again, not too much there here, but a lot of options for user to find extensions of whatever we do there. Go over this pretty quickly as well. Mooredyne, again, that's really if you want shared moorings at the farm level. So each turbine can obviously have its own Mooredyne instance for that turbine, but if you want to connect one turbine to another through Mooredyne, through a shared mooring arrangement, you need to use Mooredyne for that. And these are all the capabilities of Mooredyne. I don't know if anyone's doing that here, but see how it all connects to FAST.Farm there. It's basically getting the positions of the turbines as input, calculates the line tensions as output, and that's how it couples in. It's a pretty low level connection. And internally, of course, it's basically solving F equals MA for that Mooredyne instance. A lot of features of Mooredyne there, like synthetic ropes and seabed bathymetry and so on. But won't talk too much about that because this is about FAST.Farm. Okay, so now we'll get really the meat of what FAST.Farm is doing. Again, there's two main blocks we need to go through. One is wake dynamics, and one is the ambient wind array effects module, and of course how they get linked together. So first of all, for the wake dynamics, again, right now it's set up so it's dynamically allocatable. So we take this module and we say, okay, if there's n rotors, we have n instances of these modules. So basically one solve for every wake. And what it does is it solves that wake evolution behind that rotor. I would say this is where the most of the CFD calibration parameters are. And so overall, we've not had to make too many changes when we say switch FAST.Farm from one rotor to another, but there's a few things you could definitely calibrate better if you have an LES solution of that. And so if you really want that wake evolution to show up right, it's great to have some high fidelity reference cases and basically calibrate some of these parameters away to the reference solutions and get a better solution. So how does it couple in? Again, you can see the inputs going in there. We need to know what the position and orientation of the hub is at that time step. We need to know the relative velocity and skew angle. So overall, like where's the wind coming in? We need to know the ambient TI and ambient wind, and that's really used in our eddy viscosity model. We need to know the thrust and torque distribution for its solve, and we need to know the velocities of every wake plane. Those are calculated by other things. At the end of the day, what this module is calculating is the position and orientation of the wake planes, the wake deficit across the wake plane, and it can calculate the wake diameter, which is based on that wake deficit. And internally, it does a bunch of, there's a bunch of low pass filters in there, and those are all done with discrete time states. And then the position, rotation, and velocities are also solved with discrete time states. Everything is done, the wake evolution is done in this, what we call meandering frame of reference. So in global coordinates, it looks, looks meandered and maybe the planes are even changing orientation over time, but inside wake dynamics, it just solves it as a straight, in a straight frame that doesn't move like that. So we just track planes going downstream effectively. So you can see this sort of mapping between global and local. And that happens also in the solve. But the wake deficit is basically solved in this meandering or simple frame of reference. Oops. So some of the details here. The first bullet maybe a little wrong spot. But first of all, we use a passive tracer. So the wake dynamics tracks that passive tracer, but the actual velocities of the wake planes are solved externally. You saw it as an input to this module. We'll explain later how they get solved. But what happens here is at every time step, it says, well, what's the thrust to now on my rotor? And I compute a wake deficit from that. And then this module will again propagate that deficit downstream. Because our wake deficit evolution model is effectively a quasi-steady model, we can't throw a lot of dynamics into it. And so we basically low pass time filter everything that comes in. So all the inputs you saw coming in, like the thrust, distribution, all get low pass filtered. So we only let low frequency. So we can track small, changes over time. If you have a gust come or something, but you can't do it instantaneously because the model is really not meant for those high frequencies. Yeah. Yeah, so we'll get into that a bit more, but yeah, basically that the next turbine downstream will ingest whatever is coming on upstream, whether it's one wake or multiple wakes. And it's very much a global effect in the sense, wakes get superimposed locally, but then the turbine will ingest that and calculate its wake from that inflow. So it's not like a global superposition that Flores has. Yeah, so the first bullet is a little hard to understand until we get into more effects, but maybe we'll circle back on that. So the first model of FAST.Farm is really this near wake correction model. Again, what that's trying to do is capture that pressure gradient zone where I say I know what the thrust and induction is at my rotor, but I want to calculate it at the end of the pressure gradient zone. And usually what happens there is the wake expands as that pressure recovers the free stream. And we have two ways of calculating that wake expansion. One is a basic simple momentum theory solve. And so this model works great if the thrust coefficient is low, which means, usually critical threshold there is 24/25, so about 1. So anything below 1 basically uses this momentum theory. And that would say is the most cases. At high thrust, so between say 1 and 2, that's in the sort of turbulent wake state. We definitely know momentum theory does not work anymore in the far wake. And we've gone resort of simply fitting to an LES solution for that. You see it, I'm showing a case, so if you just take like AMR wind and you're on a CT of, less than 1, you'll get that top curve with uniform flow. But as soon as you say CT is more than 1, the wake will become turbulent wake state, and it gets a nasty mess. In the end of the day, we just fit a distribution to that to get the far wake effect. We don't try to solve the details of the far wake. So again, there's these 2 toggles in there. Those are the 2 models. And if you're in the thrust that's in between, we simply blend those solutions together. Yeah, the high thrust is interesting. You may ask, why do you even care about that? Maximum thrust, optimal thrust to be 8/9, so that's below cut out. And this really happens at low wind speed, usually at very low wind speed. Your rotor speed's running high tip speed ratio, because you're trying to not have such a large operational speed range of your rotor. And usually like 6 meters a second or below, you can often run a high thrust and then have this model kick in. But yeah, just so you know it's there. It's really not used that much, but yeah, really low wind speeds, we tend to use that model. Next model is, now I have my thrust. After that near wake correction, I need to then propagate not my thrust, my wake deficit. I need to propagate that deficit from my near wake to my far wake. And we have really 2 models for that right now. One is the original, what we call the polar wake model. This is exactly basically matching what was in DTU's original DWM model. I think it's the same model in dynamics. So it's a polar solution, axisymmetric. Basically, it solves what we call the thin shear layer approximation of NAWEA or Stokes. So it solves the continuity equation only axially because it's axisymmetric. Also solves the momentum equation. It does this with a second order Craig-Nicholson scheme. The main thing about how to solve that is how do you handle the closure? So how do you get, say, the viscosity in that model? And we have this eddy viscosity formulation that really takes 2 things to estimate what the viscosity is for the momentum equation. One is the ambient turbulence. So whatever, the higher the turbulence, the more viscosity it says is in that model. The other one is the wake shear layer. So yeah, the more higher the shear in your wake, the higher the viscosity and the quicker it will recover. And there's a couple factors there. You don't have the equations in there. You can see them in the guide, what that model looks like. But there are a few factors in there that you can play with to basically resolve that viscosity. The next model that we have is the curled wake model. So this is not axisymmetric anymore. We actually solve it on a Cartesian grid, and it's really meant to capture the deformation of the wake when you ever have skewed inflow. And you see a comparison there of the curled wake relative to LES. But effectively, yeah, the way that's solved is the skew will lead to a series of vortices, basically horseshoe vortices that get shed downstream. And from that vorticity from the vortices, you basically calculate the deficit needed to resolve that through basically solving the momentum equations. So this is work that's been, we use this really for the skewed cases. So like wake steering cases definitely becomes more important there. One thing we've had issues of is high shear and veer, because often you're doing wake steering with high shear and veer. And actually, I think this week, Manuel student from UMass will present at NAWEA on our improvements to curled wake formulation for high shear and veer. And so excited to have that feature come available soon. That also relies again on this eddy viscosity model. So those are the 2 options you got. For the wake deficit, again, polar, really simple. And same as what DTU had done originally, curled wake, a nice advancement to that. Now we step into the next main module of OpenFAST. That's this ambient wind and array effects. So if you first look at a high level, what that module is doing, it's taking, again, every wake plane that was solved in our wake dynamics model. So it takes the position and orientation of that plane, also takes the velocity deficit of that plane, and the wake diameter get from that velocity deficit. So those are sort of things it's taking in. What it's calculating is this disturbed wind field of the farm, of both the low and the high res domain. It's calculating the ambient wind in TI that's needed in wake dynamics, and it's calculating this meandering plane velocity. So every wake plane gets a velocity assigned to it, and that's calculated here in this module. One thing that's very interesting about this module, it actually has no states at all, so it has no memory, which makes the solve, much easier. It only based on those inputs and the parameters of the model, it can solve its output. Parameters in this case are really, the main thing is the ambient wind. So you have to pre-compute what the ambient wind field is, and that basically is a parameter then of this solve. So in order to do that, there's really two main ways of generating that ambient wind. There's synthetic way, like a TurpSim or a MON type approach. Kind of see, what TurpSim looks like there. It generates, basically a 2D time evolution, so 2D plus time field at a given plane, and it uses this Taylor's frozen turbulence assumption to propagate that downstream and make it a full 3D plus time field that FAST.Farm would need. But that's obviously a key limitation of synthetic model. Also, it is synthetic, so you can match your target spectra and coherence and so on, but it doesn't really resolve continuity or momentum. So there's definitely approximations there that's in its solve. MON model is very similar in the sense that it's 2D plus time, or actually I think MON is 3D converted to time through, again, a Taylor frozen turbulence assumption. Nice thing about MON, of course, is it does resolve the fundamental equation, so it does resolve continuity. A bit more expensive though than TurpSim, and a little harder to tailor to your solve. So that's one approach that we often use. I would say we tend to use synthetic turbulence for small farms. Maybe a single row of turbines would be okay, but if you're talking about a big farm effect, TurpSim can't really capture the large length scales of the farm. And so as we get to larger and larger farms, the use of LES precursors for the FAST.Farm inflow is much more important. So here we're trying to really resolve, the CFD of the flow, again, without turbines. So this is definitely a lot coarser than you would need if you put a, actuarial line in there for wind farm simulation. Other than the fact that we do need these high fidelity zones in the solves, because we need to resolve fine scale turbulence at least around the turbines. So that part makes the LES can be expensive. Obviously, once you have this solution in the flow without turbines, you can reuse that case over and over again for, I change my turbine or change my controller, or whatever. I can run lots of cases. So again, putting the burden really on the pre-processing step there. But we also recognize that's also a bottleneck now in our FAST.Farm solve is, how many LES cases do we need to run to generate some inflow? So in the future, we're looking at more of a hybrid inflow technique. That's basically saying I only need to solve this coarse LES domain, this few second time step, 20 or 30 meter time scale, get my flow around the domain in that, and then use that basically the TurboSim or MON approach for the high fidelity domain. And that's where we're going in the future to make that computational step less expensive. So that's the first thing we do is process inflow. The next thing we do in FAST.Farm is do what we call the wake overlap and merging calculation. So again, if you're talking about a region where there's multiple wakes overlapping, this is where we do a superposition approach. Again, just to clarify, I would say it's very much a local superposition rather than a global superposition. I mean, whatever wakes are overlapping that point gets summed together. But the turbine itself is really feeling the effect of the wake, and it calculates it based on that wake. So it's not a global effect where you say, I can't, to calculate the wake of turbine 5, it doesn't solve turbine 5 independently. It has to know everything upstream to do that thing. So it's very much a local superposition. So how does that work? Right now, we take that wake deficit, from every turbine or every wake that's overlapping. And we basically say we do a root sum square, which is like a continuity preservation superposition. We do that for the axial wake deficits. For the transverse, we just vector sum them. And that's how we see the effect of two wakes coming together. One thing about the solve is it basically requires that you loop through all the grid points, all the turbines, and all the wakes. And you can imagine that's a pretty big loop. If we do the math on that, that's basically an NT, where N is the number of turbines squared loop. So the more turbines you have, square that's how much more expensive that solve gets, quadratic. We actually are changing that right now. Explain a little bit in the future how we do that. Basically say, if you can pre-compute where the wake, like what area we expect that wake to be in the future, and if I can pre-compute it up front, I can make that n squared solve an n log n solve, and make it much more efficient. And so that's coming soon in version 5. So yeah, that's being worked on right now. Excited to see that. But because right now it is an n squared solve, all these loops can be done basically also efficiently through an OpenMP parallelization, which basically means because every point can basically be solved independently of everything else. So the more cores you throw at it, the faster that solve will be as well. Talk a bit about more of that scaling of computational cost when we talk about the glue code. The third thing that ambient wind and array effects does is calculate this wake meandering velocity. And the basic idea that we're doing here, you could say, well, the simple way to calculate that velocity would be to say, let's take whatever the ambient or whatever the disturbed wind is along the wake plane and just average it out. Say, well, that's the velocity it should go in. And that is one of the options we have, is this uniform weighting function that's shown in the blue on the curve. So it's uniformly weight all points, and that's the velocity that will give that wake plane. But if you know things about signal processing, say this time frequency domain transform shown there. If I take a nice step or uniform weight in the frequency domain in the time domain, that ends up basically as this jink function or sync function if you're talking about 1D. And so we've basically taken that idea and flipped it around and said, well, if I want to get a nice, clear cutoff in the frequency domain, what I need to do is spatially average with some weighting that's not uniform. And so in this case, we use this jink weighting, spatial weighting. And the nice thing about that is that on the frequency domain, then it gets a nice clear cutoff of, so only, again, low frequencies affect meandering and high frequencies get averaged out. And so we have two ways of capturing the effect of that jink weighting. We have this truncated jink that basically takes, it's the red curve shown there, is it says, I'll take that first hump, and then when it gets to 0, I throw it out after that. And then we have what we call the weighted jink, which captures the first peak and the first negative peak, and then once it hits 0 again, we throw it out. And so, because if you did the full jink, it would take wake planes would have to go on for infinite, and we don't. That would be impractical. And so, yeah, but nevertheless, as you get to say, you move from uniform to weighted jink, your wake plane needs to be wider to capture that weighting effect. So we look at our sort of guidance for how big the wake planes need to be. It's all tied to that. Assuming you're going to choose the weighted jink option, which is generally what we recommend. But, that's how it's done there. So again, we spatially average the wind across the plane, but we don't just uniformly average it. We weight it by that function. The final submodel of NAWEA is the wake added turbulence model. I showed the picture on the upper left before. So that's uniform inflow with without wake added turbulence. The main idea here is that we calculate this wake deficit, and again, wherever there's high shear or high deficit, we basically have a factor on that, and that factor then scales that deficit with a uniform isotropic turbulence, and thus wherever there's high gradient, we add turbulence in that solve, and we basically superimpose that turbulence onto the background flow. One thing we're doing quite different than I believe is in dynamics is we do that through basically a whole farm-wide wake out of turbulence domain. And so, yeah, that gives basically the farm-wide effect of wake out of turbulence. And there's implications there like that added turbulence can meander the flow a little bit more. So like a very stable case, you know, you do get some meandering because of this effect. So it's like a secondary meandering effectively from that. Just showing, yeah, a couple examples where we validated that model. The one in the middle there is against the Alpha Ventus wind farm in Germany, where the flow went through the Pheno 1 Met Tower, hit the two turbines, and with and without wake out of turbulence, because this was a fairly stable atmospheric case. With wake out of turbulence, we really were able to capture the data well, but without, we definitely underpredicted the effect. And the LES comparisons shown there, that was from a torque paper, I think last year. Yeah, so that's the main effect there. Finally, a little bit about what the FAST.Farm driver is doing. Not meant to go through all the little steps of the flow chart there. The main thing is that there's 3 modules that get parallelized in the solve. So that, yeah, imagine every sort of vertical line there is a thread on your computer. So I think my computer has like 8, cores in it. So imagine there's 8 threads there. And some of the solves can only be done on one of the threads. And then 3 of the modules we actually parallelize. So basically, the 3 things we're doing there is the OpenFast solve. So we use every thread there. So yeah, like my computer there has 8 threads, so I can do 8 turbines fairly efficiently on that farm. But if I go to 9 turbines, imagine it becomes a bottleneck because I have to basically wait for that last turbine to finish before I can do everything else. So that's, you definitely see that in the plot there too. If I have 20 threads and 20 turbines, that's great, works well. But as soon as I go to 21, it slows down. And so yeah, if I have 100 turbines, it's going to take 5 times longer than it would have otherwise. So the more threads you can throw out, the better. The other thing is wake dynamics. Again, what that solve can also be parallelized across thread. So the more threads you have, the better. Or at least you want to match it, the number of turbines. Otherwise, you have to wait. And the final thing is the ambient wind array effects module. Again, we mentioned that was an n² solve now. And you see it there in my plot. There's a quadratic function, and say roughly, I would say at 20 turbines where those 2 calculations balance out. So yeah, waiting for an OpenFast solve, whereas in solving a 20 turbine, we effect solve basically balances out roughly around 20 turbines. But as you add more and more turbines, eventually that ambient wind effects loop is killing you. We've seen that when we run 100 turbines with FAST.Farm. But nevertheless, I mentioned we're changing the way that ambient wind and array effects solve works to an n log n solve. You can see it goes from red to green. And that's going to really eliminate that bottleneck of the solve. So we're super excited to release that here in 5.0 and make larger farms much more practical with FAST.Farm. The other thing that's in this slide is the time step overview. Again, usually we say the low res time steps are pretty coarse, usually a few seconds. High res definitely subpartitioned in that, so you get a lot more high frequencies going into the turbine. Then OpenFast usually solve a much finer rate. So hopefully that clarifies some of the things happening there. One thing about this OpenFast bottleneck, you see, obviously, it's still have a big bottleneck. Even if we saw, even if we go from n² to n log n for the ambient wind array effects, OpenFast can still be a bottleneck for large farms on small machines. And so one thing we've done there is added an option for simplified turbines, which means, this case I have, say, 16 turbines there. On my machine, that would be, slow because I have to wait for the second set to go. But one thing we do have in OpenFast, in FAST.Farm, is you can say, I just want to take some of my turbines and make them simple. So they're not full OpenFast solves, they're just a simple actuator disk. And that means, if I say I just only care about loads on a couple turbines of interest and everything else, I just want the wakes, you can choose this option and say, okay, I'll make those turbines simple so they're very efficient, and then make the ones that care about fast. And that's use it to match, number of turbines to cores that you have. And you see the scaling, that part would go down in itself. Yes. maybe this is my last slide before I pass it off to Emmanuel. Won't talk a lot about calibration, but again, if you count up all the inputs in the input file that are like empirical constants, there's about 20 of them in the model. So these are the 20 you basically have to play with to get a better solution if you can calibrate them to something you know. And so this just kind of outlines how we do it. And if you want the scripts, we can share those. But usually, again, what we have is a subset of cases in LES to say, I want to match that. That's my benchmark. That's my truth. I want FAST.Farm to match that. So usually what we do is we have these cases in mind. Usually it's, I have maybe 10 LES solutions, maybe just a few. And FAST.Farm, of course, you can run a lot faster. So say I run 10 LES and 10,000 FAST.Farm simulations, and I basically do a grid search on FAST.Farm to basically get my parameters to match the LES solution. So usually we run the LES, we identify what parameters we want to change in their range. Usually I extract characteristics out of LES, like shown there, like I fit the wake meandering, track the wake deficit. I figure out what the wake meandering is, look at the wake deficit, and compare those throughout the FAST.Farm. Again, we then basically run FAST.Farm in a grid search type approach. Then we pick the parameters to give us the best answer. And so, we've done this in a few cases. Original calibration against LES was done for the NREL 5 megawatt for different, I think it was one turbine and a few different inflows and yaw airs. We then did another calibration when we introduced the curled wake model. I believe that was also for the NREL 5 megawatt. We then switched our attention to IEA 15 and megawatt turbine. Again, noticed most parameters were exactly the same, so not a whole lot of calibration had to be done, but a few parameters that we nudged a little bit, got a bit better answer. We did, also looked at a floating case, again, nudged a few things there, and also we did a case with wake outage turbulence where we calibrated those parameters. But those are what we've done. We've also done some private ones that are not public for specific clients. But again, if you have your own turbine, your own thing in mind, and you have access to LES, this is always a useful step if you really want to make sure FAST.Farm is giving you the best answer it can get. So with that, maybe I'll pass over. Well, maybe I'll pause there and ask if there's any questions before we move on to the example. Anything? Okay. Yeah. Oh yeah. Sorry.
Number of planes that you find. How do we decide on that?
Great question. Let's save it for the next section. When I'll go through the input file, we'll give really the guidance on these things. But yeah, that's definitely a key. Keep in mind, how many planes do I need? How big the plane needs to be? These are all things we'll talk about. Yeah.
More questions or? So did you, so I'm gonna ask, so this is the link. Raise your hand if you've been on that link and downloaded the zip file, or who hasn't done it. Okay, good. So try to do it as soon as you can, or if you are just not part of the workshop, that's okay. What else do I want to say? Who has a Mac? Raise your hand if you have a Mac. Do you know how to install to compile FAST.Farm on your computer in Roscoe? Who doesn't know how to do this? Who doesn't know how to have Roscoe and FAST.Farm on a Mac? You don't know. So hopefully Abhijit can help you at some point or whenever. For the first example, you don't need it, so that's the good thing. So actually, maybe during the break, or is that just a Conda install, or Conda? Is that on Conda or not? Exactly. OpenFast is on Conda, but FAST.Farm, I don't think so. Also? Okay. So it's going to be a Conda, so yeah. Who has Linux? Raise your hand if anyone has your Linux. Hopefully, if you have Linux, you know how to compile stuff. You know how to compile FAST.Farm and Roscoe. Raise your hand if you don't. You'll figure it out exactly. Good. Yeah. Anyway, so once you unzip the FAST.Farm tutorial.zip, you should get a folder that looks like this. And for the Windows users, you're going to have the 3 executables with you that you could use. You have the FAST.Farm, the OpenFast, the TurboSim. And if you are familiar with Jupyter Notebook, so that's also like kind of a requirement. Who doesn't know how to open a Jupyter Notebook? Raise your hand if you've never done this. Do you have Python on your machine though? Do you have Python? So if you're completely stuck, you can always pip install Jupyter if you know how to do this. Otherwise, you have the Python scripts here that you can run one by one. It's just not as interactive and fun as the Jupyter Notebook. But I think the way I would do it in my computer, if you have Python in your terminal, depending how you do it, I would probably do a pip install Jupyter, I think, or Jupyter Lab or something like this. In my case, I have it, and then I would do Jupyter Notebook, and it would open in the browser. If you have Anaconda, you probably need to do something different. And ideally, you get some kind of notebook, some kind of Jupyter Lab or Jupyter browser that opens up. And if you did it in the right directory, you are already in the good directory here. Otherwise, you probably need to know where you are and copy files around so that it looks something like this. Who is completely stuck at this stage? So ideally, you could open this Jupyter Notebook, and we'll work on example 0 together. And the big question is going to be who can install the OpenFast toolbox? So who has never installed the OpenFast toolbox, the Python OpenFast toolbox on their computer? Raise your hand if you have never done this. So are you familiar with pip install? Well, with git clone and pip install, or that's too much? If you're familiar, you can easily do this. The thing is, right now you need a dev branch of, I give the instructions on this tutorial. You could do git clone the OpenFast toolbox. Actually, what I'm missing here is you need the dev branch. So you need the dev branch of OpenFast toolbox. And you can install it like this. To save you time today, so that would be the way to install the OpenFast toolbox that has all the Python tools that we use for FastFarm and OpenFast. To save you time today, what you can do, if you run in this directory, you can just rename. I gave you the toolbox here in that directory. You can just rename this to OpenFast toolbox. And basically, you don't even need to install it. Python will know that all the Python tools are in there. That's the quick hack. In the long term, you should try to learn how to install the OpenFast toolbox. And that would be the way to go right now. It's on the dev branch of it, dev branch. The idea of this tutorial is we have a bunch of FastFarm examples that are on the OpenFast toolbox. So I'm going to click on that link here. It's like the second link that shows up. The first one is for the toolbox. It's our GitHub repository where we have a bunch of tools for working with OpenFast and FastFarm. This is how the repository of the toolbox look like. And if you go on the second link, you have in OpenFast toolbox FastFarm example, you'll see some examples. And actually, if you go to the dev branch here, you'll see I've updated them last week. And you'll find the examples 0, 1, 2, but those are more advanced examples. Okay, so the tutorial I'm going to go through today is simpler than those examples. And it's step by step. So if you allow me, let's just go back to the notebook. You can read the instructions. It's basically saying what I just said here. And on a Jupyter notebook, to run cell by cell, you do Control-Enter. So it's always good to run all the cells. The first one is just importing a couple of packages. You don't really need all of them. If you don't have pandas, it's okay for now. Ideally, you do pip install NumPy and pandas if you don't have them. Who is completely, and then you can try to load the toolbox and we'll see who is completely stuck at that stage already. And for me, nothing works. Okay. It should, if you run the second cell, you do Control Enter on the second cell. Hopefully it tells you, okay, the toolbox was successfully loaded. Who hasn't reached that stage? Who cannot run even just the second stage? Because then we cannot do the examples. No one dares to raise their hand. There has to be someone that couldn't do it yet. Okay, raise your hand if you have run the second cell. Yeah, there's a lot of people that are not honest here. All right, okay. So, quick, where are you stuck? Tell me. What did you say? You're downloading the toolbox or the tutorial, the zip file? Using pip? Okay. Maybe I'll go next. So someone else. Yeah, you. Yeah. Yeah, so if you have Windows subsystem, so if Python is only in Windows subsystem for Linux, I don't know how you could get the browser. You probably need to install. There's some stuff you need to do for WSL to pop it out. But ideally, install Python on Windows. That would be the best. If otherwise, you can just follow what I do and try this at home later. Another question, someone else that is stuck. You definitely need to precompile all the executables. So those hopefully should work on every of your machines. If you have Windows, you could open a terminal in that folder and try to run it. You can try to run, hey, open fast. Oh, that's not. In general, you always need some executables that are precompiled. Yeah. Yeah. If you want to install the OpenFast toolbox, you get the development version. Otherwise, you take this OpenFast toolbox that I give you in the tutorial, you just rename it to OpenFast toolbox, and then you're done. You can move on. If you're stuck in the pip install, just rename this folder into OpenFast toolbox. Before it was called OpenFast toolbox _ rename. All right. Can I get some hands up of who is able to run cell 2? Raise your hand. It's getting a tiny bit better. Can you try if you just rename? I'll give you a few seconds. It takes time to get started. Ideally not before 2:45 or something, but maybe 15 minutes would be great.
Finally got.
Should I walk around and help some people?
Yep. So, can you rename the folder? Can you find where in the middle? Where is the folder? Can you rename the middle part? Rename this. Okay, for now, just rename it. First the box, rename it. Remove the video. Spawn that. That's only tell me that was. You don't even need to reload it. The other two. And you get install the computer. It is already okay. So how do you Python? Do you have Python? No. So if you don't have Python, because so you can self-installing Python. Should I ask or something? Do you have Python? Yeah, and try that, but you don't look at the world to open it. So it's can you, Yeah. It's not. Here. Is that how you say? Okay. Control. Up here. Okay. So try going back to the side. Okay. So on, so this try to be and you're not feeling much forward. How about you? Hi. Wait, I also answered to Brian? Right, well, it's kind of running something in the background right now. Did you write everything? You just interrupted the camera? Did you start with W? It doesn't turn W. No, it's. That's it's so. It's not good at all. Okay, we okay. Yeah, you can go to the make sure and then starts you can have the same context.
I think so. Yeah, it runs the first and second. So,
I just think,
yeah,
it's sort of like it's.
yeah, the idea.
Fast which is
This back on the first.
So. I get right from the. Yeah. It's given to be Windows system back. I already checked which system is it's going to each of the browsers.
Nice thing. Here, will we use it?
Yeah, that's your starting with the. Oh, you got it. Yeah.
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 Okay. Yeah, so it's yeah, but it's
Okay.
so.
Then don't worry about it.
Yeah, the 70s for
Running it to go, that's maybe that's the best.
right, yeah, no, just go control and so.
Yeah, that's right. The second step, it works. Okay. Who else? What you where are you going? Try the same thing. Well, you don't have time. It's okay. It's trying to tell me. So, generally, you need to. So, see here. Okay, do you have anything else in the system? I'm trying to see if you can still and send invite to have that. How about you? What's else? Young investors, office work, yes. Who else need help? And because you have this, so yeah, so probably basically somewhere between something in the time where it is. I don't get it. If you know, I don't know where you are. Documents, so probably yeah, so the community, you know, use it. So that you know, Jupiter price particular. They'll, I provide to feel that's still getting people, but first example, they don't need it. We set the library, say you'll have to buy the libraries. It's not good. Yeah, real. Mac. Ah, you have Mac. Ah, yeah, so it's normal. Did you try the DY? Amazing that works. You can buy that for the library, but it's okay. You can
Okay, we have at least a bunch of you. Okay, who got the okay for the toolbox loaded? All right, that's good enough. That's 2, 3 missing. That's pretty good. So the toolbox has a bunch of Python tools to help us deal with the FAST.Farm setup. Because if you look into the template files, this is basically, you have all the files needed for one FAST.Farm simulation. A lot of you are familiar with OpenFast, so there's an FST file for the turbine, and there is also a default FAST.Farm file for the FAST.Farm simulation. Like most OpenFast input files, there's a lot of lines with a lot of comments, and so it takes time to get familiar with all of them. And if you've ever tried to do your own FAST.Farm simulation, there's all kind of parameters for how big the grids need to be. Jason mentioned there's 2 grids in FAST.Farm. There's the low resolution and the high resolution. And usually the first user, if you try to set it up yourself, it is actually very difficult to set up those parameters. It's about placing the grid at the right location. The other parameters that are difficult to set is the time step. I mean, not too difficult, but it's going to be a function. The quality of your simulation is going to be a function of your time step and your spatial resolution. Depending on which model you use, you need to make this right. And the FAST.Farm toolbox is going to help you set those for you. My piece of advice, so in this template folder, if you want to try, you can try to take the OpenFast and the FAST.Farm executable, copy paste into your template folder, take the FAST.Farm, the OpenFast, copy paste into the template folder, and try to open a terminal in this folder if you know how to do this. You open a terminal in the template folder where you have now the OpenFast and the FAST.Farm. And you can try running OpenFast like I just did. You do OpenFast -- version, or you can even not say anything. Actually, that doesn't even work. I don't even know. It's like -H. Yeah, exactly. Anyway, this is just to make sure your OpenFast works. It tells you, okay, this is the syntax to run OpenFast. And my first piece of advice before you run any FAST.Farm simulation is like, make sure you have an OpenFast setup that works. A lot of you, it is way easier to debug an OpenFast setup than a FAST.Farm setup. So make sure you know how to run OpenFast. You have a FAST.Farm setup that works. Your initial conditions are good. Your controller runs well. And right now the setup is set for Windows laptops. And I'm using Rosco, the DLL that does the controls. So if you're using Mac or Linux, you'll have to change the servodyne.t, which is the file that is being used in that case. And this is pointing up, if you open it, it is pointing to some DLL that is a local directory. I need to show you this better. Sorry about that. At some point in line 77, it's opening the libdiscount rosco.dll. So if you're using Mac or Linux, you have to compile your own DLL of Rosco. And then in the servodyne, you will need to change this to point to the .so file, the shared object that you have for a library. If this is too complicated for you and you really want to just try to make it run, let's just get rid of servodyne at the moment. You open your wind turbine file, the FST file of the wind turbine, and you can set comp servo to 0. And then you don't run with the controller, okay? And hopefully you can run now you can use your OpenFast with your FST file. And you won't see this running Rosco thing showing up because it's not using the DLL anymore. You can see it doesn't tell me running Rosco. Now it's running at constant RPM, constant rotational speed. So step 1, always make sure your OpenFast simulation run. And step 2, you can try what I advise. I gave you a file here, FAST.Farm for initial debug.fstf. This is a file, I think I printed in the terminal later. It has a huge domain. It's like a huge domain, and it has a huge low res box and a huge high res box, so that if you have a big turbine, it's going to fit in that box. And that's the second thing you can try is like you have your turbine that works, you put it in this debug FAST.Farm file to make sure it kind of runs through. And this should run, I think if you tried right away, you could try running that file and it should work. It's pointing to, you can see on line 39, it's pointing to the windturbine.t.fst. And you could try in the terminal to run that file. So you do fastfarm.exe and then the fastfarm for initial debug.fstf, and hopefully fastfarm runs. That's kind of the first step, making sure you know where to place your turbine and how to. It has a very simple grid. If you open this debug file, it has only 2. So it has nothing, right? So JSON is nothing because it's constant, it's uniform inflow. It's not even a grid, it's just a box that has 2 points. And it's huge, it's several kilometers wide, and the high res is also huge. This is good for debugging, making sure you know how to start setting up your FastFarm simulation. This is not really needed at this stage, but I just wanted to let you know. So if I keep scrolling, this is instructions for how to install on Linux and Mac. If you're using Windows, then I have this little check to make sure I know where the FastFarm executable is, the TurboSim executable is, and the Rosco DLL. I don't think so. What the trick is, where is the Rosco input file? That's the problem. The .in file of the Rosco input file. But so you're going to see the toolbox takes care of it pretty well and make sure things are at the right location. Okay, moving on a tiny bit. So if it doesn't work, if you're using Linux, you need to point to wherever you installed FastFarm or the Mac. You probably need to change that path or copy the executable. On Windows, everything should work out of the box. And it's trying this code is actually trying to open the library and making sure you can call it, and it works. Anyway, so you don't need this right now. We're going to need it for the example 1 that we cover later. Right now, we jump to example 0. Imagine you have a FastFarm setup. A colleague gives you a FastFarm setup, which is this file that I opened earlier. Can I make this bigger for you? Yeah. Okay. So template fastfarm.fstf. Let's check if the file exists. The file exists. But then I'm calling the function plot FastFarm setup that I imported earlier. And it is giving me 2 red messages saying that it's not happy about the bounding box of the high res, and the bounding box of the rotor for turbine 1 is not fully contained in the high res grid. So it's plotting those grids here below. In gray, I have the low res. In blue, I have the high res, and you can see how the high res is not contained in the gray box. That's the first error message. Second error message is the rotor is not fully contained in the high res box, and now you can see it. So this is like the top view. I have X and Y. This is the XZ view. So it is actually it's another. It is like a side view, and this is the front view. And you can see how the rotor is not fully set up. And that happens. If you didn't have this plot FastFarm set up, you would have to think of how to set those parameters, or you would try to run FastFarm and it would give you an error like this one, like velocity outside of grid bounds. If you've ever used FastFarm, you've seen this error before. Yeah. Yeah. So what? So it can still come if you do it manually. If you use the toolbox is making sure that you're never going to have this error. So you're going to like the toolbox. It takes a while to install, but then it sets up OpenFast for you so that those errors don't happen. Right now, this is just for you to try to understand a tiny bit the input, or if you want to become a bit of a hacker and modify those inputs yourself, you can keep running the cells. I'm going to show you how you can modify manually this input file. So you can run the cell, I don't know how much now, 7 maybe. It tells you what are the parameters in the main FAST.Farm input file. For instance, we have the X low that shows up. We have the X0 low. So those are like, if you run the next cell, you can print what are those parameters, which is basically the same as opening the file and looking at those values. And if I keep going, the main question for you, if you go to that cell that has some red text below, say modify the low resolution below. So you uncomment the cells, uncomment those lines, and try to find how I should set NY low. And I'm just going to say 30 at first. I think it was 31. Okay, so it was 31 before. I'm keeping 31. I still have a problem. My low res is too small in the Y direction. So you can increase this to, I don't know, 61. Try running this again. Now all of a sudden our low res grid is better. Okay. Of course it's simple, but you have to think, how big is my delta Y? How many points do I need? It takes time. So those functions are here to help you. And the same, I'm going to go quick, just example 0. We still have the problem that the rotor is not fully contained in the blue box, right? We need the high-res resolution to surround the rotor. So maybe I'll just quickly stop. Who is about that? Who is not able to run this cell with putting 61 here? Raise your hand if you're not, if you're completely stuck at that stage. Okay, good. So I'll move on. Keep going. Basically, you can go through this tutorial at home also. Now we have a problem of the high-res box. If you open a FAST.Farm file, I'm just going to do it for you. This is the FAST.Farm file that we are debugging right now. Around line 39, you see where the turbines are defined. In that case, I just have one turbine. And this is where the high resolution of the turbine is defined. This is the origin, the 0, the origin of the box, and the delta X is the resolution of the box. The last parameter missing is also the number of points in that box. So a combination, right now we have a problem in the vertical direction. If you look at this, clearly I don't have, there's a problem with the vertical resolution of the high res. I don't cover the whole rotor. So I either need to have more points in the Z direction, or I need to increase my spacing. It's one of the two, or a combination of the two. So if you run the cell here, it basically shows you the input file, the line that has the turbine. And I'm going to help you out. I mean, you can try both. On the next cell, you can uncomment and play with either NZI, which by default is NZI is 15, NZ is 15. Sorry, so you can put 15 here. That's the default value, and here the default is 10. Another thing that is a bit slightly annoying is you need to figure out in this wind turbine dictionary what is the index of the column that I need to change, and it's column number 9 to change delta Z high. Okay, so it's an array in Python. It's 0 indexed. So this is the setup how the cell should look like for the baseline. And Z high equals 15. Wind turbine 0. So that's the first wind turbine. I only have one. Column number 9. This is my delta Z high, basically. And I still have the problem right now. I should still have a problem like this. Do you know which parameter you should change? Is it NZ high or DZ high for that case? You said DZ high? It is DZ, yeah. So clearly we want to have the same resolution in the Y and Z. It makes sense, right? Horizontal, vertical, we probably don't want to change the resolution. We probably want to have a square box around the turbine with similar resolution in the lateral and vertical. And if you look at the input, I have delta Y high is 20, whereas my delta Z high is 10. And so this is what we can change here. We can change now my delta Z high. I'm going to set it to 20, and hopefully it's enough to put the turbine in the box. Nothing prevents you from having 40 or like, I don't know, 20 here or like a bigger, and you can see the box is going to be bigger, but with the same delta Z. So I advise you when you have a setup to try the plotting it so that you know where your boxes are. It works with multiple turbines, multiple FAST.Farm input, and then if you want, you can rewrite this file that we modified. Actually, we modified this FSTF object, and now you should be able to see a FAST.Farm new file that showed up. And ideally, I could compare it. I could take it, put it next to my template, and compare it with my FAST.Farm file. Oopsie. So here I'm comparing the FAST.Farm new on the left and FAST.Farm old on the left and FAST.Farm new on the right. And you can see we changed delta Z, NY low from 31 to 61. And Z high, well, I put 20, but I didn't have to. And if I scroll a bit, delta Z high has changed from 10 to 20. So when working with OpenFast, it's good to know to have a file comparison tool. Okay, I'm using WinMerge on Windows. If you have Linux, try to find a file comparison tool so you can take two files and compare them. Always very useful. And I think that's it for example 0. It's just to get you started with the toolbox, and after that, we're going to try to run more complex setups. Any questions, or if you're stuck, now it's the break, right? So I can also help you during the break a bit. But any questions so far? It's all about finding the size of the boxes. Right now, you're lucky. You have no idea the FAST.Farm toolbox exists, so it's going to set up those boxes for you. When you have 100 turbines, if you have to manually find the delta Z, delta Y, it will be a pain to do. But back in the days, this was very useful because we needed to know. And if someone gives you a simulation, it's also good to just plot the setup to see what's going on. All right. There's no question. Let's take a break and raise your hand if you need help right now.
We'll come back at 3:05. So take your 15 minutes.
Still the recording?
Yes. Actually, yeah. Can you stop it or not?
You have to do it.